Hello everybody and welcome to the second 22nd lecture of MHM for 2780. As I mentioned previously, we covered all the materials necessary for this course so far. So today I'm just we are going to solve one example together, and on Tuesday we are going to have an online session that if you have any concern or question regarding the administrative aspects of MHM for 2780, you can be online during that time and we can chat and we can talk about it. So it's not going to be lecturing or anything related to the science, but provide you an opportunity with talk directly to me to speak about the concerns or anything that you might have. Regarding the preparation for exam, I try to basically cover every angle that a question might be asked during the exam in my lectures. So you have lots of materials that you can go through and learn. For example, assignments. All the examples that I solved during the lectures. Test 1, test 2, basically I mean semester test 1, semester test 2. So you have lots of materials to work with. Okay, the most important thing that you need to do is having attention to details. Don't make small mistakes in a way that, for example, sometimes reading wrong number from the table, calculating Reynolds number, for example, wrong, and after that everything after, like your Nusselt will be wrong, your H will be wrong. So try to avoid those kind of mistakes. And please keep in mind that you are not allowed to use any other than your textbook during the exam. So of course we are not going to be it's very difficult for us to enforce it. We are relying on your honesty in this case, and of course your the forms that you sign before submitting the final answer. Just that even you are not allowed to use your notes during the exam. So it's just like textbook. By having access to that textbook and going through all the lectures, you should be able to get a very, very good mark, because I covered basically everything for these four chapters. So it's almost impossible to see one question that is not being covered in a way or another, or some part of it in a lecture or in assignment or in semester test 1 and 2. Okay, but let's solve another example, and this will be our last one. Here we are going to try to solve question 11-131 of the textbook together. Saturated liquid benzene flowing at the rate of 5 kg per second is to be cooled from 75 to 45 by using a source of cold water flowing at 3.5 kg and 50 centigrade through a 20 millimeter diameter tube of negligible wall thickness. So let's start from here. I have 47 temperature, I see it here. I have 45, so the temperature decrease. What does it mean? It means that saturated liquid benzene is my hot fluid and my cold fluid is water. Cold fluid. For hot fluid, I have m.h, I have th in, I have th out, and for cold fluid, I have m dot, I have just one of the temperatures, so I don't have TC out. Can I calculate TC out based on the other three values that I have? Yes. Why? Because we know that I can apply the energy balance, and if I have three temperatures as well as m dots, I should be able to find the fourth one, so it shouldn't be a problem. So I can do it. I'm just like brainstorming now. So basically I have all the temperatures. Three are given and one can be calculated easily. The question is also saying that the diameter of tube is 20 millimeter and the wall thickness is negligible. The overall heat transfer coefficient of heat transfer is given. The specific heat, or CPH basically, of liquid benzene is given. The capacity ratio and effectiveness remains the same. So it means that the temperature difference won't affect it. Determine the heat exchanger surface area for 4 different configuration. A. Parallel flow, B. Counterflow, C. Shell and tube heat exchanger with 2 shell passes and 40 tube passes, and D. Cross flow heat exchanger with 1 fluid mixed liquid benzene and other fluid unmixed water. So basically it's looks very simple. All the information are available. So the only thing that we need to do is to find out the surface area of heat exchanger for 4 different configuration, because we want to see that which one, like which of those 4 different configurations is the most efficient one. Most efficient one in terms of giving us the same temperatures but with the less surface area. Okay, let's start from the first point that we mentioned about finding the TC out. So let me go to the next page and write the energy balance. So I know that Q.H is M.H CPH TH inlet, th outlet, and q dot cold is equal to m dot c cp tc out minus tc in. Okay, so we mentioned that m dot h, we have it, is equal to 5 cph. The question is giving us, so we have it, is 1839 joule kilogram Kelvin. th in is 75 and th out is 45 degrees. On the other hand side, for hot. For cold fluid, we have some information as well. We know that m dot c is 3.5 kilogram per second. Cp cold is equal to 4187 joule kilogram Kelvin. Tc in, cold in, we have it. What number is that? 15. Tc out, we don't know, so we need to find it, but we know that it's higher than 15. So from balance of energy, q dot h is equal to q dot c, so m dot h cph th in minus th out is equal to m dot c cpc tc out minus tc in. We don't have this one, the rest we have it. So basically then T out basically is divided by m dot c cpc. We write this, sorry, h th out plus tc in. If you calculate that one, the outlet temperature of cold fluid is calculated to be 33.82 centigrade. So in order to use, I'm just like going to use epsilon into u. Maybe after that you can use LMTD method and see if the results are the same, and we can you can compare those results. Okay, we don't have enough time today to do both, but for if I want to use, let me write it down, epsilon NTU method. Regardless of the configuration, I need to calculate some things like the heat capacity rate of cold fluid, the heat capacity rate of hot fluid, the capacity ratio and stuff, those like basic values. Let me first calculate them, and after that we can start calculating the surface area for every single configuration that the question asked us. So the heat capacity rate of cold fluid, I should see capital C, is m dot c cpc. So basically is 3.5 multiply by 4187 joule kilogram Kelvin, which gives us 14,654.5 watt per Kelvin. So it's C. The heat capacity ratio of hot fluid, which is m dot h cph. Sorry, I said heat capacity ratio, heat capacity rate. Sorry, heat capacity rate of hot fluid. We just like put the numbers that we have. Joule kilogram Kelvin. But as you can see so far, we didn't get any numbers, so all of those numbers were given. So it was very simple for us. So if I calculated, the answer will be 9,195 watt per meter. Okay, now I have the heat capacity rate of cold fluid. I also have the heat capacity rate of hot fluid. So the heat capacity rate of hot fluid is minimum and cold fluid is maximum. Okay, so we can calculate the capacity ratio, which is C divided by C max. So it's 9,195 Kelvin divided by 14,654.5. So the answer will be 0.627 is lowercase c, which is capacity ratio. Okay, now let's try to start calculation based on the first configuration, which is parallel flow. Okay, so epsilon, we know that it's Q dot divided by Q max. So, and we said that okay, Q dot max, we go here, we say that the Q dot max is the cold water. So I just like, so basically it's C minimum in minus T C in, and on top we have CH THI minus TH out. Just talked about correlation before, so it's not a extraordinary thing, and at the same time we know that the heat capacity rate of hot fluid is the same as the minimum heat capacity rate. So basically epsilon will be equal to 75 minus 45 is divided by 75 minus 15, which make it 0.5. So now we have two values that we might need for the next steps, and epsilon is 0.5. So then for non and what we are using, okay, epsilon NTU method. Okay, now let's say we know the value of effectiveness. We also calculated the capacity ratio. Now what we need to do is to find the number of thermal unit. Sorry, we need to find NTU. Can we find it? Yes, there are plenty of correlations in table 11.5. The only issue that we might face is which correlation I need to pick. So what do you think? Could you please go to table 11.5 of your textbook and let me know which correlation you think is the best to pick? But of course for this specific configuration, which is parallel flow. Okay, so if you go to table 11.5, you can see that for parallel flow is suggesting to use this correlation. So number of thermal unit is equal to minus ln 1 minus epsilon 1 plus c. This is lowercase c, which means the capacity ratio 1 plus c. Okay, so we have the value of epsilon 0.5, we have the value of capacity ratio 0.627. so if we put in this simple correlation, the number of thermal units will be equal to 1032. Okay, now we have NTU. There is a very simple correlation that relates NTU to surface area. So AS, basically, if I want to write it down, so is NTU C minimum divided by U. What is U here is overall heat transfer coefficient. Here for this example, we were lucky that the overall heat transfer coefficient was given. Otherwise, we had to calculate it. But let's say it's not given. How we are going to calculate it? We solve one example. Before, first you need to write a correlation for overall heat transfer coefficient. Normally in that case, if you are not dealing with fouling factor, the only thing that you need to do is the convection heat transfer coefficients, both sides, as well as the diameter and thickness. So it's very simple to write that correlation. The only problem is how to find the convection heat transfer coefficients. Sometimes they will be very complicated, because first you need to find Reynolds, you need to find Prandtl, and after that, based on the Reynolds number that you have, you need to find out what kind of flow you are talking about. Is it like laminar? Is it transient? Is it turbulent? And after that, you need to go to the right chapter to find the right correlation, because besides that, correlations, they have a limitation as well, because the majority of them, they are semi-empirical correlations. So based on the values that they did the experimental work, they just like suggest the correlation. So, and they say that you can use that correlation when the Reynolds number is between these two, or when the Prandtl number is between that two. So when you find the right correlation for Nusselt, you find the Nusselt, and after that the heat transfer coefficient can be calculated easily based when you have the Nusselt number and K, which is thermal conductivity. When you calculated the H, after that you repeat the same process for another H, because as I said, we need two heat transfer coefficients to calculate the overall heat transfer coefficient. So you put those two values into the correlation that first you wrote for overall heat transfer coefficient, and you calculated. But in this example it was really easy. Why? Because the overall heat transfer coefficient was given. Okay, so if we use this correlation here, we have U, which is overall heat transfer coefficient. We calculated number of thermal units to be 1.032, and the minimum heat capacity rate, we said that it's the same as the heat capacity rate of hot fluid, so we have it as well. So if we put everything together, the surface area will be, so number of thermal units mean divided by U, overall heat transfer coefficient, so will be 1.032 multiplied by 9195 watt Kelvin divided by 750 watt to Kelvin, which was given in the question itself. So this will be equal to 12.65 square meters. So it's for parallel arrangement, parallel flow arrangement. But after that, if we go up, the question is asking parallel, determine the service area. So the question is asking B, the counterflow. So what's the difference between this basically parallel and a counterflow? So different configuration will not change the heat capacity rate of hot fluid. It won't change the heat capacity rate of cold fluid. It also won't change the capacity ratio. Is it going to change the effectiveness or epsilon? No. Epsilon will stay the same as well. Okay, so what will change then? The only thing that will be changed is the correlation that we calculate Nusselt. Okay, so if we go back to the table 11.5 of our textbook, you can see that for epsilon equal to 0.5, and from part A, the Nusselt NTU, the number of transfer units, can be calculated by using this correlation. TU is equal to 1, C minus 1. C here is capacity ratio, ln epsilon minus 1, C epsilon minus 1. Okay, so a little bit more complicated than the correlation that we use for parallel flow. So if we put the numbers into it, we can calculate that number of thermal units is equal to 1, 0.627 minus 1, ln 0.5 minus 1, 0.627 0.5, basically that's a -1. So if we calculate that the number of thermal units will be 0.85, and after that if we apply it into the same correlation as surface area is equal to number of thermal units multiplied by minimum heat capacity rate divided by U, which is overall heat transfer coefficient. So basically it will be 0.85 multiplied by 9195 watt Kelvin divided by 750 square meter Kelvin. The answer will be 10.42 square meter. Not a big surprise. Why? Because we knew that that is something that should happen. Why? Because we mentioned that for counterflow, which was our second arrangement, always you should expect with the same temperature coming in and out, you should expect a more efficient system compared to that of parallel flow. So now let's how about for 2 shell passes and 40 tube passes? Any idea? So I think we need to go back to table 11.5, because for the previous two situation we just went to table 11.5 and everything was fine, so we do the same. But there is like a problem here, because the epsilon that we calculated is 0.5 basically. We calculate that one. This is just valid for 2 shell passes. Okay, so now how we can extend it for 40 for 2 shell passes and 40 tube passes? So we need to use F is equal to C epsilon minus 1 epsilon minus 1 divided by to the power of 0.5. so it will be 0.627. so this is 7 minus here C epsilon multiplied by 0.5 minus 1, 0.5 minus 1 to the power of 0.5, so F will be equal to 1.172. We know that the effectiveness of heat exchanger in case of 1 shell pass, so 1 shell pass effectiveness of heat exchangers heat exchanger. This one easily can be calculated as epsilon 1 is equal to F minus 1 F minus C, so basically 1.172 minus 1, 1.172 minus 0.627, and the final answer will be here 0.315. Again, now we need to find number of thermal unit. If we do that, number of thermal unit, if we go to again the same table, we can find that there is a correlation, but we need to keep in mind that the correlation can be used when we are dealing with the exchanger which has one shell pass Now we can add the 40 tubes passes as well, so won't make any huge difference. So NTU I'm just like put it 1, so it's equal to 433, 0.433. So since for multiple passes NTU 2 is 2 NTU 1, but let's say if it was 3 passes, 3 shell passes, it would be 3. 4 shell passes, it would be 4. So here, because we were dealing with 2 shell passes, we did that. Okay, now when we have all the information, let's start. Then number of thermal units 2 is 2 multiplied by TU1. What is NTU1 is the number of thermal units for 1 shell and 40 passes basically. So NTU2, which is the basically the value that we need is 2 multiplied by 0.433 is equal to 0.866. We mentioned here that what is the value of NTU1. Okay, so now we have that one. By having the number of thermal unit, the surface area will be 10.62. So now we have seeing that okay, this shell and tube, basically heat exchanger, is more efficient than parallel, but is still less efficient than counterflow. So now we have just one configuration left. If we go to table 11.5 with epsilon equal to 0.5, we can find, I'm not going which correlation I used, please go and check it and see if you can get the same result. So number of thermal units will be equal to 0.909, and if we use the same correlation as the 3 last values, the surface area will be equal to 11.14 square meter. So as you can see here, the smallest value that we get was for counterflow. So in this case, counterflow was the best to choose. Sorry, why? Because it has the least surface, least required surface area. Yeah, basically that's it. It was very simple example, but I wanted to just show you how does it work, and in terms of like a different perspective or views on on questions related to heat exchangers. That was it. So we are done with everything technical regarding MHM 42780. I'm just like going to upload your semester marks on Tuesday as well, and if you just like see that your mark is lower than 40, you know that you can't write the final test. Thank you so much for your attention during this week, and keep well. Bye bye.